Okay, so last chapter we worked a lot with polynomials. This chapter we're going to work a lot with exponential functions. Here's the difference. X is now in the exponent, and we have a constant as our base, as opposed to our polynomials. Our x was the base, and we had like a constant as our exponent. Okay, so this is an exponential function. X can be any number. A is not, however, going to be 1. Why can A not be 1? 1 to any power is 1. Okay, so 1 to the x is just y equals 1. That's not an exponential function, that is a line. Okay. Okay, so we're going to talk about the graphs probably before lunch. And then when we get back from lunch, we'll talk about the number e. So a to the x. Exponential growth is another way to describe a number to a power. A number to a positive power. Okay, this is exponential growth. Okay, we have an asymptote here at y equals 0. Okay, y, I don't even have a base. Our base is a to the x. How do we automatically know that our y-intercept is 0, 1? Jackson. Okay, and number 2, the 0 power is 1. So no matter what the base is, as long as we're talking about the parent function, our y-intercept is going to be 1. Okay, so help me out. Will, what's our domain? Yes, all real numbers. We can put any number in that exponent no matter what. Okay, Amanda, what would our range be? Okay, I have a question for you because you said negative infinity to 0. Okay. You answered my question. Okay. 0 to infinity. We only have values from 0 to infinity. Why would that make sense? Can we take a number, a positive number, and raise it to a power to get a negative number? We cannot. Okay? Because remember, negative powers mean we just take our number and put it in the denominator. So everything's going to stay positive. Okay? Would you describe this function as increasing or decreasing? Increasing. We have exponential growth. Okay, so we're always increasing and never decreasing. And like we talked about earlier, our y-intercept is always going to be 0, 1 for the parent function. Okay, we are going to work with some shifts and transformations. Now you're excited. Okay, turn to your neighbor and describe what the graph is going to look like when we make the exponent negative. What if it is a to the negative x? Turn to your neighbor or your pod, whoever you're sitting by. Cannon, what's it going to look like?
It'll go down.
All right, we're going to have what we describe as exponential decay. All right, we are going to be always decreasing and never increasing. Okay, the only thing that changes is a reflection, right? We still have a domain of all real numbers. We still have a range of 0 to infinity, and our y-intercept is still 0, 1. Okay, we have this asymptote here at y equals 0, saying, hey, we can't go past this. Okay. Now that I've shown you these graphs, how many of you vaguely remember graphing these? Okay, so I'm going to show you what I expect out of these graphs. We are going to think of the parent function and then transformations if we have them. Okay, so let's talk about what I would expect out of a parent function graph. Okay, we're going to work with f of x equals 3 to the x. For a parent function graph, where did we say the asymptote was? Where? Y equals 0. So I want to see that drawn in and labeled, especially if it's like on the axis. It's hard to see you draw in, so it'd be a good idea to label it somewhere. Okay, then this is what I want to see. I want to see these 3 points when x is -1, 0, and 1. What is 3 to the negative first power? 1/3. What is 3 to the 0 power? And what is 3 to the first power? 3. Okay. Those 3 coordinates kind of have a nice little pattern. Okay, 1/3, 1, 3. -1, 0, 1. Those are the x values that I always want you to use for a parent function, no matter what you're graphing. -1, 0, 1 are the x values that I want you to use for the parent function. Okay. And then we would graph those 3 points. Oh, there we go. There's the graph. Okay. Shouldn't take you long to graph. Now, chapter 1, we did all of our function transformations, didn't we? We really didn't do much of it. Well, we did a little bit of it at the beginning of chapter 2, but that kind of felt like we were still in chapter 1, right? So I want you in your pod to talk about what those do to our function. What are the transformations? Don't write anything down. Just have a discussion in your pod about what A, H, and K do to your function. 1, 2, 3, go. Okay, it sounds like things are winding down. Pod 1, what does A do?
Like for H and K.
Like for our graph, like if we had 3 to the x.
Okay, so like A would make the slope bigger. Like it would, if you put the, like if the A is trying to be in front of, okay, I thought that was like, I guess another A, and then you can, but A would be like a shrink or stretch the graph.
Okay, it'd either be a stretch or a shrink. What kind of number would we want for a stretch? Greater than 1. You gotta have to remember that for your roller coaster this weekend, right? Pod 2, H. Okay. Pod 3, K. I kind of like that explanation. Okay. Changes your y-intercept. Okay. We could also describe K as what kind of a shift? An up or down shift, okay? Which is going to affect your y-intercept, okay? Very good. K is not going to be your y-intercept, though. Is there a question?
Where's the 4? sorry.
Is that better? Okay, I'm sorry about that. Okay, if the negative is out here in front, what kind of reflection do we have? Which one? X. If we have negative 3 to the x, it's going to flip it across the x-axis, as opposed to 3 to the negative x is going to flip it about the y-axis. Okay? Now, when we talk about h and k, okay, let's look at a different number. This is considered inside of our function, so this is like a shift to the right, while this is after our function. This is a k, this is a shift up. Okay, just so you can see what that looks like with the exponential piece. Okay, because it's going to look a little bit different. You know, last time we were in chapter 1, we would kind of look for parentheses for our inside the function. You're not going to have parentheses up there. Okay, whatever is in the exponent though, that's going to be affecting your graph horizontally. So this is what I would expect to see from you. Okay, if we were going to graph 3 to the x plus 1, I would want you to consider your parent function 3 to the x. We know that we have the points negative 1, 1/3, 0, 1, and 1, 3. If we wanted to graph y is 3 to the x plus 1, we're going to take each of those coordinates and shift them which direction, Molly? Left. Okay, we need to go left 3. So if I take these points and shift them, yeah, it's definitely left 1. Shift them left 1, then these become negative 2, 1/3, negative 1, 1, and 0, 3. Where is our horizontal asymptote? It remains at y equals 0. If there is not a vertical shift, then it is not going to move. Okay. Think about the parent function, those 3 points, and shift them. Now, some of you are going to draw each of these, or some of you are going to write each of these XY charts. Some of you are going to think about this in your head and then write this one down. I don't really care what works for you is best, okay? But I do need to at least see this XY chart so I know what coordinates these are, okay? And this is something we're doing without a calculator, okay? Go ahead and write down this example. This is what we will do after lunch. We'll do this example and talk about one more thing before we talk about base E. So go ahead, enjoy your lunch, and I'll see you when you return. Ryan, can you get your project? Continue recording. All right. Let's go ahead and talk about this example. That -2. What is the -2 doing to our parent function, Henry?
Shifting the down.
Okay. So this is a shift down 2. So if we think about our parent function, y equals 3 to the x, I want you to think of the points -1, 0, -1, 0, 1. There we go. Okay. And we're going to take those points and we're going to shift them down 2. So that's going to affect your y coordinates. So if we take those coordinates and shift them down 2, this becomes 1, 1. This becomes 0, -1. What does -1, 1/3 become? -1 and 2/3? Okay. Okay, our asymptote is usually at y equals 0. Since we had a shift down 2, where is it now? Y equals -2. Sarah, what's the domain of this function? Good. What's the range of this function? Kelsey? Good. -2 to infinity. We're above the axis, so -2 to infinity. Okay. Any questions about these graphs? Okay. Let's talk about a couple where we don't actually graph them. 4 to the x is our parent function. And then these are the two that I want to discuss. 4 to the x minus 2 and 4 to the -x plus 3. So I'll give you a moment to write them down. Then I want you to take about a minute to a minute and a half and decide within your pod what the transformations are from parent function to each of those. 1, 2, 3, go. Okay. Pod 5. This first one.
Right.
Do you agree with pod 5? Yes. Okay. Pod 6, this one. Reflect y-axis, and then what? Agree or disagree? Agree. Any questions about those? Okay. If I were to ask you to graph them, I would want you to think about the parent function, -1, 0, 1, but now since our base is 4, our y values would be 1/4, 1, and 4. If our base was 10, it would be 1/10, 0, and 10. Okay, adjust these y values based on whatever your parent function base is. Okay. All right, so now we need to talk about the number e. Yes, I know e is a letter, but it is also a number, the number e. E for Euler, this is called the Euler's constant. Okay. Those of you who are interested in mathematicians. Okay, so E, we call E the natural base. Okay, that's why we have the natural logarithm that we'll talk about tomorrow. Okay, this is probably one of the most important bases. Okay, and we see it more when we deal with logarithms than we do with exponents. E is an irrational number, much like pi is an irrational number. And we approximate it like 2.718, blah, 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 blah. Okay, it's irrational, so the decimal is going to keep on going forever without a pattern. Well, I mean, we could have like a February 7th. Whoa, we wouldn't have anything like 8, right? Like the pi is well, but we could say like February 7th. We can think about it. If you remember it for February 7th, we'll celebrate it. Okay, let's talk about what the graph looks like. Okay, the graph, we are still going to have y equals 0 as our horizontal asymptote. Are you looking up in your calendar? Okay. Okay. We know 0, 1 is going to be our y-intercept. When we plug in 1, we get E, and we said E was 2.7. When we plug in -1, we get 1 over E. Can somebody approximate 1 over E for me? You may want to know where your E button is on your calculator, so it would not be a bad idea to get them out. You're going to need them pretty soon anyway. .367, right there. And can everyone find their E button? Okay. So, what do we use E for? Here's why E is important. Compound interest. Okay? If we have interest compounded a certain number of times per year, this is the formula that we use, where A is the amount after so many T days is probably what it's going to be. Okay? Or years, excuse me, year. T is time in years. P is the principal. N, how many times it's compounded per year. And R is our rate. Remember, rates are percentages, and so we convert them to decimals to use in our formulas. Does this look familiar? Unfortunately. As long as you can remember the formula, it's pretty simple to use. This is the formula. Okay, so like I said, A is the amount after so much time has passed. Okay, that's usually, we're gonna plug numbers in and get A. Principal, that's how much we start with. And how many times it's compounded in a year. Annually would be 1. Monthly would be 12. Weekly would be 52. Okay, rate, that's a decimal, and then time. The hardest part about this is just going to be remembering the formula. Okay? Now, you keep mentioning PERT. Yes. Yes. You keep mentioning PERT. What's the difference between this and the formula for PERT? PERT is catchy. PERT is continuously compounded. So instead of being compounded only a certain number of times per year, this is continuously being compounded. Okay. When do we use things like this? Okay. Investments and loans are the biggest examples. Okay. Loans, if you cannot buy your car in cash, you can take out a loan. But you have to pay interest on that loan because you're taking time to pay it off. Okay, so interest, you have to pay what the car is worth plus some more due to interest. Okay? Or if you invest money, your money will accrue interest in a positive way for you, where you're making money off of where your what kind of account your partner's in. Okay. Are any of you making car payments currently? Okay. Do any of you talk to your parents about either buying a car or investing money? Do you guys ever talk about that kind of stuff at the dinner table or in small talk? No, I think small talk, but okay. These are things that are good to talk about before you're like thrown out into the real world. Okay? So, if you are investing money, you want to make a lot off of the interest. So you want higher rates and compounded more times. Okay? If you are loaning money, you want a smaller rate because you don't want to be paying as much on top of what the car or the house or whatever it is already worth. Okay, but here's the example that we are going to model with those two formulas. So we're going to invest $12,000 at an interest rate of 9%. Now it's going to call the interest rate an annual interest rate. That's just how they're named. That doesn't mean that's how many times it's compounded. A rate is an annual rate, okay? Find the balance after 5 years if it is compounded quarterly versus continuously. While you're writing this down, we're obviously going to need a calculator for this, but we're not going to need a calculator to graph exponential functions. Your quiz and test will be non-calculator and calculator, two different portions. So when you practice graphing, no calculator. When you do this stuff, calculator. All right, $12,000, what does that represent? Okay, that's our principal. All right. If 9% is our rate, what are we going to plug in for R? 0.09. Okay. If we are compounded, let's look at this. 5 years, what is that? That's T. If we are compounded quarterly, how many times per year is that? That is 4 times per year. So, A equals P times 1 plus R over N raised to the NT. Okay. So we have 12,000 times 1 plus 0.09 over 4 raised to the 4 times 5. Please use your fancy schmancy calculator to your advantage. Don't plug one thing in at a time. Okay, let me get my calculator up here. Okay, you can put this in all at once. Just be careful with your order of operations. 12,000 times 1 plus 0.09 divided by 4 raised. You can't put 4 times 5 as your power. You have to put 20 or parentheses 4 times 5. But I think we can take 4 times 5 in our head and be okay. All right. So after 5 years, our investment is now $18,126.11. Let's talk about compounding continuously. Continuously means we are going to use PERT. A equals P E to the RT. Once again, put everything in your calculator at once. 12,000. Here's where your E button is, right here, second ln, right next to the 4. 0.09 times 5, notice how that's in parentheses for your exponent. Okay. So we should get $18,819.75. Which one makes us more money? Why? Okay, the more times you compound, the more interest you're going to make. Okay, so if you're investing money, you want to have an account that compounds more often than not, because then you make money off of the interest more times. Okay. If I give you a problem that prompts you to do 2 different things, like n times a year versus continuously, if your continuously is not a higher number, you have done something wrong. Go back and look at your calculator work. Okay. Okay, I have one more thing I want to talk about, since we are working with exponents. And that is a problem that looks like this. Okay, there is something called the one-to-one property in exponents, where if a to the x equals a to the y, what do we know about x and y? They would be equal. So if you look at this problem I wrote up there in blue, what could we do so that we could use that one-to-one property? I'm going to call it a name. Okay, make sure that those bases are the same. So Gabe, how could we rewrite 8? Okay, we could rewrite 8 as 2 cubed. And that gets raised to the x plus 1 power. Okay, so now we have 2 to the 5x equals 2 to the 3x plus 3. Now we have the same base. Both are being raised to the exponent. So what should be true? 5x equals 3x plus 3. Or 2x equals 3. So x is 3 halves. Questions on how we did any of that? Yes.
Will you give us a problem where you can't do that? Like,
Not until we learn, or not until after we learn logarithms. But if, the problems that you will see this evening, you will be able to write them in similar basis. Okay? All right, so here's your homework. I'm gonna go ahead and pass out the gold sheet, so you can just look off of those for your homework. Let me stop the recording.